In this demo, I will show you how to run analytical queries and machine learning on hundreds of terabytes data, which could be coming from a variety of sources using MySQL HeatWave Lakehouse. First, we will start with an Aurora instance running in AWS. A snapshot of an Aurora database is exported to Parquet files, which goes into S3. I am going to copy the location of these Parquet files and provide it as an input to HeatWave Lakehouse. Next, we will create a HeatWave Lakehouse mapping. Here is the console for MySQL HeatWave on AWS. HeatWave instances are running on AWS and there will be no data moving out of AWS. We are creating a HeatWave Lakehouse mapping for the exports from Aurora. We specify the S3 URI of the Parquet files as a data source and define a table name. This mapping invokes AutoPilot. AutoPilot uses advanced machine learning techniques to automatically determine an appropriate mapping of the S3 file to an in-memory representation of HeatWave. We will create another mapping for 100 terabytes of TPCDS files stored in a CSV format. The data format is CSV, and header extraction is enabled. AutoPilot does not simply rely on header information, but scans the data in a very intelligent manner to create a mapping. For instance, how many attributes there are, and what are their names, data types, and precisions. We have created Lakehouse mappings, and here is the list of tables. You can see some of them are from S3 and some of them from MySQL InnoDB, and all of them are visible from the same console. Before loading the data into HeatWave, we need to provision a cluster which can accommodate 100 terabyte data. For provisioning, AutoPilot can help you determine an optimal cluster size without any guesswork. AutoPilot runs machine learning and predicts an exact number of nodes needed. In this case, AutoPilot predicted we need 57 terabytes of memory to load 100 terabyte data, which requires 222 cluster nodes. We use AutoPilot estimation and provision a 222 node cluster. This took about 12 minutes. With the cluster provisioned, we can load the data into HeatWave. The data is loaded in parallel into the cluster, and loading of 100 terabytes data took about 2 hours. Now the system is ready to run queries. The query we are going to run is one of TPCDS queries. This query looks at the sales for various products for a given day or a week of this year and compares them with the same time period of last year. This query is a moderately complex SQL query with four-way join, group by, and order by. Executing this query returned the results on 100 terabyte data in just 36 seconds. HeatWave also supports real-time analytics, which means if we update one of transactional tables in MySQL and rerun the query, we will see the updated results in real time. We are going to update one of the tables in MySQL. Then rerun the TPCDS query. We see the updated results as expected. What is more interesting is the execution time drops from 36 seconds to 24 seconds. The reason is because AutoPilot learns from previous queries and provides information to the MySQL optimizer, which then can create a better execution plan. So the system gets more intelligent over time. Now on the same cluster, we are going to run machine learning. Here we have a bank marketing dataset stored in S3, and we are going to create a machine learning model. All we need to specify are a training dataset, output column, and machine learning task. And optionally, we can specify an optimization metric. AutoML automates the ML pipeline, such as pre-processing, figures out optimal algorithm, the right set of features, and the optimal hyperparameters. It creates the ML model and stores the model inside the database without the data or the model ever leaving HeatWave. For the chosen model, we can run explanation to see what are the attributes that influence the prediction. In this example, explanation shows the duration of the call which a salesperson made to a customer is a leading indicator to the customer's buying decision. Now we run prediction on a test data set. First column shows the predicted outcome, while the second column shows the real outcome. For a specific prediction, if you are interested, there are built-in local explanation and what-if analysis tools to analyze why we got the predicted results. This concludes the MySQL HeatWave Lakehouse demo. If you are interested in learning more, go to oracle.com/mysql.